Fun business here. Can hide. There's a way here. Hide floating meeting controls. And hide you guys. Okay, so it's pretty good. So basically, I'm using this. This is a Strobel book. I don't want to go to the beginning, but it's online. It's linked there. You have to put an F at the end to get it to open. And this is kind of part of the. Hi, glad you could make it. Two people.
Where is everybody?
They're all on. Like a bunch of people are online. Yeah. So anyway, it happens. Anyway, so there's this paper. I found some papers. Actually, I spent a lot of time on some other paper like this. Spent a lot of time on this sticky Rouse model paper, which is something that's popular. Like people are making networks, like a rubber network. So you'd have like sulfur here that would cross-link, and then you'd have a polymer chain. Then you can form a network, and then they're putting in these functional groups that can make a network or unmake a network. So the idea is, one point was that they wanted to make self-healing rubbers. Like rubbers you can't recycle because the whole thing's one molecule. So the only way to recycle it is to burn it, basically, or rip it apart somehow. So they're making now rubbers that have linkages that can be unlinked. So this, and it turns out like there's a theory of Rouse flow that has to do with chains and networks. And then there's this is talking about sticky Rouse model for networks. So they put in a sticky linker. And you kind of get 2 relaxation times, but this gets like really complicated. It starts out pretty simple, but then it gets to be like too complicated. So I spent like all day yesterday trying to read this thing and figure out what they were talking about. It makes sense, but it's too much for the. So I linked it there. It's linked on the. You can look at it if you want. There's a lot of the sticky kind of network stuff around, especially in Japan. Like in Japan, this is like a big deal. It's one of the main things people are studying, putting in polymers now, like releasable networks and things. So, and then in the US, there's a lot of self-healing materials. You break it and it'll bond itself back together again. So that's popular too. It's the same stuff. It's just that the Japanese are really doing it for rubbers with the tire industry, and in the US, it's kind of like there's no products that people are looking at with it. So it's a bit different. Anyway, so this paper I found before that paper, this paper is a lot simpler, and I thought it was too simple, but it turns out it's okay. It's like pretty good. It's just not as interesting as the other one. So this one just has to do with, they just take a Rouse polymer and they stick these filler particles into it. It's a simulation. So they're using this thing called LAMPS, which you can download onto your own PC and use if you want. They have like a big, it's from Sandia National Lab. You see a lot of people use it. You can basically this web page has like an intro that explains how to use it. Then there's downloads. You can download it to your laptop or whatever, and then you can go through this whole thing if you want to. It's basically like a course. And in the end, you can like write papers, using the LAMPS. So it's not, I think it's not that hard to do. It's just some kind of time investment, a little bit of time investment. So anyway, that's what they're using with this paper. So they make some particles, like they're making nanoparticles. So they make rods, they make sheets, and they make this kind of cluster thing, which they call a nanoparticle. So they call that a nanoparticle. That's a rod, that's a sheet. Then they also look at they look at, oh, it's in the supplemental. Right? So they also look at these kind of things, like they take these variation in the nanoparticle, like have different cluster size. Then they put these into a matrix that they don't show of polymer chains that are 30 beads long. So their polymer chains are also beads. The difference is these beads are more rigid than the polymer beads. So this stuff, and then once you have that, so in the terms of the simulation, so it's called a coarse grain because there's no molecules, and it's just spheres. And then see, oh, here they show in the supplemental, they show the polymer chain. It should be 30 of these blue beads. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically 3 times that is what their polymer is. So they throw in these particles that are about the same size. Then they're going to look at how that impacts the Rouse dynamics of the thing. So that inside this lamps, so you can set up your thing. You have these 30 long bead chains. Then you have the particles. Right, so you have to have some kind of rules to live by. So these are the rules that they live by. So first off, like there, so let me go over there. That worked. Scrap paper was of course I was like advertising to be students for it. And then nowadays it's packed, you know, so you don't have to advertise. But anyway, so you have the string.
Hey, Dr. Beaucage, FYI, for folks online, we're just seeing the paper.
Right. Yeah, I haven't. Can you see my hand now?
No, I mean, we're seeing like the academic paper.
Oh,
Hey, Mike.
Yeah.
You can actually, in the little pop out that's in the corner, you can hit the button and swap your shared screen with the video, and it resolves it.
All right. So I guess it's just me.
Yeah, you can do it from your end if you want to.
Got it.
how does that work with the recording though? I wonder how that works with recording. Anyway, it's worked in the past with the recording, right?
Yeah. Don't worry. It's just me.
Okay. All right. So anyway, we have like we have 2 rules, right? For if you have a sphere, you're gonna have like the force is going to be the velocity times the friction factor. We have the Stokes law is 6 pi, the solvent viscosity times the size of the sphere. And then we also have the spring thing is that the force is the position times the spring constant. So then you also have the change in energy. I think he calls it E here. Sometimes it's called U. dx is the force. Okay, so if you have this one, you can say that the energy is going to be like, if you integrate x dx, you get x squared integrated divided by 2 times k spring. Okay, so you have that energy. That's kind of what you expect for a spring. And then the energy so this thing is only used in the Langivine is going to be a force balance. You're going to have like the friction factor times dx dt equals the spring constant times x, and then you put in a random. So usually, sometimes they divide by the friction factor, and then this thing becomes. Then they just have a random thermal motion. It's like a del parameter. It just pulses up or down. That's the Langivine equation. It's basically a force balance between the 2, right? So, and from this, like you get dx over x, that gives exponent. That gives ln of x, and you get the exponential minus t over tau from that. Right? Dx over x integrate gives you the logarithm. We have t over here. And tau equals the friction factor of the spring constant. Or if it's a bulk thing, it's going to be the viscosity over the modulus. This relaxation time. So that's kind of like, and that gives you this behavior like x versus time. It's got a pulse and then it's going to decay down. That's your thing. When it's time constant is when this thing reaches e to the 1, like when t equals time. That's e to the 1, which I think is like 0.27 or something. So when you get to 1/4 of the height, that's when you're at tau, that equals tau. When you're at e to the 1 for the value. Anyway, so you'll see, so you see this kind of spring constant, that's a rigid spring, just like that, right? If you have a polymer chain, it's got so there's two kinds of spring constants in this paper. So you can see the paper, right? So that means that's the springs, x squared times the spring constant, that's the energy. Right? There's no divided by 2, but basically he just calls it K2. Right? So that's just a normal energy for a spring. And that's what he uses for the beads. He says the beads are connected by this spring. And then the polymer, though, the polymer bonds have a finite extension. In other words, if you fully extend the polymer, so each of these beads in the Rouse model. So in the Rouse model, we got the chain. We're going to separate into Rouse units. Each Rouse unit is a chain, right? And that's got a finite extent L. So in order to fix, so it's not a spring if you fully extend it. So you put in this 1 plus x over L squared, and then you have your x, and then the K spring here. So this thing, so when x equals L, or this is minus, sorry. So when x equals L, that goes to 0, and then this force goes to infinity. In other words, when it fully extends, it goes to infinite. Right, so this accounts for its finite extensibility. So that's called the Feeney potential. Put that into the energy thing. So it's got to do with, you can't extend the thing forever if it's a polymer chain, if it's a nanoparticle. So that Feeney thing, if you integrate it, you end up with ln of this thing. So that just comes out. That's like an integration by parts. Or not, no, it's not integration by parts. It's just a substitution. So you have, what is it? You have x over 1 minus x over L squared. And then this is d energy equals, and then there's a dx here. So you say, what do you do? Let's see. This thing is y, dy equals 2 minus 2 x dx over L squared. Right? And then so you have x dx. So this thing is like y to the minus 1 dy. Right? And then dy over y is ln of y. Right? So that's where you get this. That's where you get this ln of this thing's y, like the subscript is y. So ln of y, and then that's the extension. So like instead of this thing squared, it becomes ln of that thing. Right. So these are both like spring functions. This one has a finite extent, and this one doesn't. This one keeps being the spring, no matter how much you pull it. Right. So those are two rules. This is like common. This is just stuff that's built into lamps. Like it's just like, you want to have the normal things. You say yes, you get these. That's just how it is. And then there's also this. So the bonds can also flex. Right. So there's a spring constant to the flexing of the polymer chain bonds. So you put that in. So you put in flexing. So it's the same kind of thing. It's like the change. So it's going to be like proportional to the flex, the projection of the angle, cosine of the angle, and then it's squared because you integrated it. So it's the same thing as the spring constant, it's squared because you integrated it. Then you get the energy for the bond flexing. So this is like the polymer, this is the filler. And then that's part of it. So that's each structure within itself is going to be subjected to motions, right? Like vibrational motions due to KT. And it's going to generate these energy changes. The system's trying to get to a low energy. Right? So you're moving, everything moves around, and you calculate the energy for the whole system for everything in it. And it's going to have, I think it's like 40 by 40 40 bead by 40 bead size box cubed, right? So it's like 10 million something. They end up with some huge number of these beads within this box. The box is just made of polymers, and it's made of these fillers in it. Right? The fillers are kind of rigidly stuck together. And then they have to interact with each other. So every time they move, the positions between the beads changes, and there's a 612 potential, which is also like you just check the box. So it's got short range attraction. This negative means it's attracting, right? And it's got a long range repulsion. But the long range repulsion ends at this cutoff size. So you don't have to integrate over the entire box. You just integrate up to the cutoff size, which is like so many bead diameters. Right, so he's got the potential for everything happening, and then he just changes this prefactor. So there's three things that can happen. Polymer bead can meet a polymer bead, so that's a PP. Polymer bead can meet a nanoparticle, that's a PN, and a nanoparticle can meet a nanoparticle, that's NN. So there's three kinds of these energy prefactors. Are given values of 1 for PP, 1 for NN, and 3 for PN. So 3 for PN means that the fillers don't like the polymer as much as the polymer likes the polymer. And the filler doesn't like the polymer as much as the filler likes the filler. So the filler is attracting itself, and the polymer is attracting itself, and they're kind of repelling by a factor of 2. There's 3 minus 1. So it's kind of a situation where you're pushing the two apart. You know, you could change that if you wanted, but that's how they did it. They fixed it at that through the whole thing, which makes you think. And then, all right, so this brings up a problem with this paper, you know, that doesn't make that much sense. So if you have, so plus energy means bad, and negative energy means good. So if it's plus 3, that means bad. Right, so it's got an additional 2 whatever energy units for the, so that means that if you have that, like the polymer shouldn't interact with the filler, right? They just should repel each other. So you should have, if you just let this go to equilibrium, the filler should just go and make jump like a whole phase of filler. The polymer should just make a phase of polymer. So that's kind of a question that I have for this paper. Like, how is that possible? You know. So you have anti-dispersion, like from this. It means the things are going to try to attract each other. All right, so that's that business. Let's see. So the nice thing about this lamps is it has everything built in. Okay, so you set that up, and then you can go and reach equilibrium. So he goes and does an equilibrium with this thing. He uses this, he says somewhere in here how he does it. After he uses this constant number, constant pressure, constant temperature, equilibration. Oh, he sets the pressure to 0, sets the temperature to 1, and he lets it equilibrate. And then he also does a constant volume and lets the pressure float and lets it equilibrate. And then, so the system's equilibrated. And then inside this simulation, it allows you to put on it like a flow through it, like a shear flow. So you can take your simulation box and like have a shear flow, and it does that because it has like mirroring at the edges. You know, so you got, so you have your box. So you have your box, I forget how many beads. It can't be 40, it's gotta be more than that. Say 40. then when a bead goes over here, so say these beads are fixed, and the top beads are moving at velocity of your shear rate. So, so that bead dy going down to 0, that's your rate of strain, right, for the system. When this bead goes to here, it re-enters there. So it's got this mirror symmetry. So everything that goes out goes back in on the other side. So you don't lose anything. So you can do a flow measurement then, right? And then you get the shear. You can see what kind of force you have to apply. This has an area, so you get a stress from that too. Then the shear modulus is going to be the stress of the strain. The shear modulus or the viscosity is going to be the stress of the strain rate. And so you can get the viscosity, you can get the complex viscosity. That gives you the storage, complex storage modulus, and you get G prime, G double prime. So it's possible to get it in a simulation if you have a big enough box. And you want to have the area to be something much larger than one of the beads. That's kind of the rule for this thing. So it could be something like macroscopic. There's some problems with it, but basically you can do it, and you can do it at home on your PC, on your laptop. Like anybody can do this. Right, so it's all packaged. And he finds out, like, so this is called the pain effect. So if you stretch a thing, so if you take a balloon, right, and then the first thing a lot of people do is take the balloon and like stretch it out before you blow it up, because it makes it easier to blow up, right? So the idea is that the balloon's got silica in it, silica filler. The particles are all making a network in there to get its strength. Otherwise, it would rip apart. In fact, without the silica, the rubber would just shatter, would just rip, like a pencil eraser. So anyway, so with the filler network, keeps it together and prevents tearing of the rubber. But that filler network also makes it hard to stretch. So when you pull on it, you're kind of ripping apart that filler network. And then if you leave it, it'll reset. Like the filler network reforms. It's a time dependence to it, but the time is like on the order of minutes. So basically you can do that, stretch it, and it blows up easier. So that's what he's doing here, is like going across strain. So he's got like 0.01 strain. It's like less than 1% strain, goes up to like he goes up to a large strain, like 1. It's like stretching at 100%, like what you do when you stretch the balloon. When you go through that with the stuff, you find out that the modulus drops. So that's breaking up the filler network. And this is an oscillatory shear. So they have that box, but they're going back and forth, right? So it's oscillatory to get the storage and the loss from the frequency of it. This is at some fixed frequency, which he doesn't mention here. But so anyway, so that breakdown, that's called the pain effect. And then when he has no filler, there's no pain effect. When he has filler, there's pain effect. It's to different extents. If he has clusters, rods, or sheets, right? The sheets and rods can act the same. And then the storage modulus doesn't show that. So the storage modulus is basically constant. So it's only the loss modulus doesn't show it. The storage modulus is the only thing that shows it. Right? And then this is against size of the particles that you're putting in. So it's kind of interesting. You can do that with a simulation. This kind of packaged software, that anybody could use. You can just do your measurements on it. Right? So that's why this is so attractive. Like, you don't need any money to do this. Like if you have a computer, and then this is free to download the lamps. So you can just generate papers, like just make up as far as your imagination can go to make the things, whatever it is you're making, then you can just write the papers, right? So that's what they're doing here. So you can see why there's some appeal to this. All right, so then it gets into this business of P. So the modes, these are the modes of the Rouse thing. So this is like the main meal here, the main course. All this other stuff is appetizer. So get rid of that. I'm gonna use up quite a few of these old advertisement things. So this is the deal for the Rouse. There. right, so this is, all right, so the rouse is pretty painful. And if you look in, like, if you look in the Colby Rubenstein Polymer physics book, they do it in one page and they just give the answers, and it's pretty confusing. It's confusing no matter where you look at it, okay? If you look at the original Rouse paper, it's confusing. And then there's the people that have written up like that other paper, it's all tensor math, you know, so it gets to be, and they talk about the eigenvalues of the matrices. So you got to have a serious course on tensor math, like more than the intro to tensor math, to figure out what's going on. And then, so basically the best thing I've found is the Strobel book, which is a complicated book. People note that it's hard to read, but it's the most simple explanation that actually gives you something you can put your teeth into. So I gave the citation of that. And then in the homework, I asked you to go through that section, get to the point where he comes up with that the relaxation time goes with the molecular weight squared, which is, and it also goes with the modes p to the -2. Okay, so you have to know what a mode is, basically. So if you take a guitar string and throw it on the floor, it looks like that, right? If you put it into the guitar, and then all of a sudden it's got modes. So it's got this mode that's called the 1 mode. If you take the guitar and throw it across the room, that's the 0 mode. That's translation. Okay. The first mode is that mode. The second mode is like this. And then you can imagine you can break it up into 3, however many you want. Right? So those are modes. Modes of vibration. And each mode has a different energy. Okay, so it turns out if you blast this thing with kind of white noise like KT, most of the energy is in the lowest order modes. Like the sound you're going to hear, if you wanted to identify what's the tone of that guitar string, you would say it's the first mode. No, it's like E. Right? In fact, all of these are going to be E. It's just going to be octaves up in E. Like if you put your finger in the middle of the string, you'll get the next octave of E. If you put it like up here somewhere, you get some really high octave. If you put it, anyway, you can get this really high pitched tone out of a guitar string if you put your finger in the right place. People do that. You know, it's like, so anyway, there's these modes, but most of the energy is in the low order modes. That's true also of a Polymer chain. Okay, so this was done by Debye, again, like for heat capacity, like how does a crystal store heat? So he says that the crystal is like a string and it's got modes. So you got, except that there's like beads in this thing. So those beads are the atoms in the crystal. So Rouse said that a Polymer chain is like that. So the chains like this, unless you put some constraint on the ends. Okay, so the constraints on the ends that you put, first, the simplest constraint is you make it into a cyclic and then it's constrained. And then that will have modes like around that go with like the molecular weight. So anyway, they'll have modes around the ring like that. You can also take the chain and fix the ends. Like if you look in that other paper, they're talking about a network, so things aren't actually fixed at the ends with some functionality. So then this thing behaves like a Rouse dynamics in the middle, right? And then if you put in these sticker things and you change those dynamics, so you can imagine that would get kind of interesting, I guess. But the problem is that anytime, anyway, that's really complicated. You know, this is much simpler, believe it or not. So anyway, that's kind of the overview of this thing. So on top of that, we're going to write the Langivan equation. Right? So we have the friction factor, and then we have the velocity. Friction factor times velocity gives us force, and that's going to equal the spring constant. And then we have this thing that we have bead. And you don't call them I because we're going to end up with imaginary numbers. You can't call the beads I. So in Strobel, he calls them L. I tried to write this out using I, and then I get to the complex number part and I realized why he used L. So he calls it L, and then L -1 and L +1 for the beads. So the positioning of these is going to be L minus 1 minus L, and L plus 1 minus L. And if you have, and you're considering both of these, so if you move here, it's going to change the spring here. If you move there, it's going to change the spring there. So they're coupled like that. So you have to have the position of L twice. Then you have position at L plus 1, and then plus the position at L minus 1 times the spring constant. And then if you divide this by the friction, by the friction factor, then you just add in this fluctuation if you want, but you don't have to. Right, and then this thing, so we're gonna have, this is Z, not X. So we got that thing, and this is gonna give us, so you have that, that's a differential equation with these kind of various positions in it. Right, and then you say that the solution to this is going to be a wave. So a wave solution is going to be this. We already know that this thing is going to have a relaxation time like that because it's got a spring and it's got a friction. So it's going to have this kind of exponential T over tau behavior to it. So we propose a solution. Right. It's going to have this e to the minus t over tau to it. So the position z of L is going to equal, it's going to be proportional to this exponential t over tau. Another exponential that has to do with, because you're talking about bead L, right? So if this wave is going up and down, the position z of L is going to be different than L plus 1 by some phase factor. In other words, the phase of the wave that shifts it. So like the angular dependence of the sine wave that's going through it. So it's going to have this phase shift that has to, and the phase shift is going to be times the position, and it's imaginary to make it into like a cosine wave. So e to the IL is like cosine of L del plus I sine L del. So this thing is basically a cosine wave, and it's got this phase factor, this del that shifts it. Right? So del, so the solution to this thing has, so we have here 4 parameters. We have z, we have t, then we have tau, tau's here, and then we have del, del's there. L is the index and I is the imaginary number. So I have 4 parameters, and we have 2 equations. So you can kick off z and t, and then we just have tau and del. So from those 2 equations, we can get a relationship between tau and del. Right, that's kind of the way this works. So you can solve that. Like you can plug this into that, solve the differential equation. Right, and I'm not going to do that. It's different. You can do it, but you need to know that 2 minus 2 sine of del L equals cos squared of del L. Right, but anyway, we don't need to worry about that because we aren't going to solve the differential. We're just going to give the answer. Right. So, and then it's done in Strobel's book. So the answer is that 1 over tau is 4 times the spring constant over the friction factor. So the tau is the friction factor over the spring constant. That's what we already know. Like tau's the friction factor divided by K spring, or the viscosity over the modulus. Right? So, and then sorry, this is cos and this is sine. You can work this. If you find the solution is 2 minus 2 cos del L. That's sine squared del L. So it's sine squared del L. Okay. So that's the solution of the relationship between tau and del. If you plot that out, so you can plot tau to the minus 1. So this is just sine squared, and then del L, del of 0, sine of 0, 0. So tau is infinity there. Right? And then it's going to go to this value of like K spring over the friction factor, and it's going to follow like a sine squared, which kind of looks like a sine. between minus pi and pi. Right, so there's no modes in this. This is just kind of the string floating around. It doesn't have any modes. This is just kind of how it could store energy. Okay, so this is the simple version of this thing, right? So then you say, so I'm going to tie the two ends of my thing together, and I'm going to do it by making it a cyclic because that's the easiest way to do it. Because then L equals L plus the number of units in the Rouse units, which are sections of the chain clustered together. So my position L is going to be the same as the position. So Z of L is the same as Z of L plus NR. And so that means that my chain, that my values of del or it means that my modes, let's see, my modes, the modes are going to be 2 pi, are going to be the modes times 2 pi has to equal the number of units times del. So del is per unit times the number of units gives me the full thing, which is going to be the number of modes times 2 pi for the full cycle. Right. So that means I have a relationship between the number of modes and del. In other words, I can define what del is. Del is the modes over NR. NR is a big number. In other words, it's how many Rouse units are in the chain. You don't know what that is, but basically it's a lot of numbers. It's a lot of them. Right. So chains, conceptually an infinite chain, so NR is like something close to infinity. You break that down into subunits. So there's a lot of subunits. So basically this number is a small number. That's important because sign of a small number is the number. Okay, so like sine of x equals x if x is small. You can kind of see that if you look at sine. Basically around 0, it's going to be just a straight line. I mean, sine, if you expand sine, it's x plus x squared over 2 factorial. So the power thing drops out and it's just x. The series expansion for sine. Complete term is x. Sine of x is x if x is small. So anyway, so with that, then you can substitute this sine squared del L for just del, right? So you have 1 over tau is del, and del is this m over n, right? And then k spring is also 1 over n. So k spring from, if it's a polymer coil, is 3 kt over nl squared from our Gaussian thing. So you have another n from k spring. So that n and that n gives you n squared out of this thing. So it means that tau is going to be proportional to n squared. That's one of the things you can get out of that. And then also you can get, because this is coupled, right? So this is del squared here. So and del has m in it, so it ends up being that tau goes with m squared. Tau goes with m to the -2, which is what they use in the paper. So that's the point I wanted to get to. Tau goes with m to the -2, and this thing is broken up into modes, right? We're only considering the low order modes because that's where all the energy is. All the energy goes, and you can calculate. Strobel calculates the energy in each mode, and he says that mode 1 has 90% of the energy stored in the chain. So basically, you can forget about all the other modes. And that's definitely a case where del is a small number, so you can forget about the sine squared, and then this all falls together in whatever package you want. All right, so that's the first part. It asks you to go through that. So you can't get this from a lecture, I don't think, but we can maybe get a warm, fuzzy feeling about it. Maybe not. But anyway, he goes through this thing exactly the way I did it, but maybe better. So he's got the equation. That's a Langivan equation. That's 3 kt over nl squared. Then he proposes a solution, and then does that twist to get the sign squared. And then he doesn't actually mention that because del's small, you can just sub in del squared here. But that's there. And then he says that if it uses cyclic condition, then you can get this expression for del. He does it for linear too in here, but basically the cyclic's good enough. Then it breaks it down to these modes. This is exactly the way Debye does this for heat capacity. All this up to this point is you could pick up a book on physics of heat capacity, and you'd find exactly the same plots. Like it's the same thing, you know. So up to a certain point, everything is the same. It's just kind of copied over. It's complicated enough that no one can tell, you know. So anyway, so it asks you to follow this up until you get to the M thing. So in our simulations, go back to this thing. He can't easily change M. He's got an M of 30, and that's all he's going to do. He's not going to do like molecular weights and see if he gets Strauss behavior to do the normal plot. But he can pick out the different modes of vibration from his simulation. So he has a way to figure out which one is which mode. So then he can do this plot, and it's supposed to go with the modes to the -2, and P is the power, P is the mode, P is M, Strobel's M is P. So this is mode 1, mode 2, mode 3, mode 4. Supposed to go with mode to the power 2, so he plots log, and he looks for a slope of 2, and he finds it. So he can pick out the modes from his simulation. He finds that behavior. So that's Rouse behavior. And he finds that it's got Rouse, basically Rouse behavior for all these things. So he's got pure polymer, that's Rouse. Nanoparticles, meaning nanocluster, Rouse. The other things are Rouse also. But as tau gets bigger, gets larger, as he changes the shape of the particles that he's putting in. So the sum means there's something going on, like so what's going on with this thing? Like he gets a longer relaxation time when he puts in his filler. So how does that work? So he's got, so you have, say you have like we talked about hydrodynamic, like is, oh, sorry, yeah. So talked about hydrodynamic, like is it going to be a Rouse chain where it's alone, right? And then, or is it going to be this kind of chain? So it's alone, you have the friction factor, it goes with N. These are the other two things that come out of the Rouse. So one is that the viscosity goes with the molecular weight. The other, the friction factor goes with the molecular weight. The diffusion constant is KT over the friction factor, so that goes with 1 over the molecular weight. And what's the other one? Is there anything else? Diffusion, viscosity, and then tau. Tau goes with molecular weight squared. Right. So normally you'd say that viscosity kind of goes with tau, but basically viscosity is a bulk measurement. So you have to have like an area. So to get you need to know how many chains cross an area. So you need to multiply this by the concentration of chains, which is the concentration divided by the molecular weight. So that N2 goes to N1 for viscosity. That's also in Strobel, the later part of Strobel. This is complicated though. So you take a molecular thing like the friction factor, and you want to get a bulk thing. It involves like geometry. You have these chains, they're randomly positioned in space. You want to cut an area through that. So it's a geometric problem. You have to figure out how many of those chains that you know the number for cross that plane. That's got to do with the density of the chains. You know, if you're talking about one chain, there's no density, it's just that chain. But if you're talking about a bulk sample with an area, there's a concentration of those chains. So you have to have this concentration term, which, and its concentration of chains, it's going to be like the mass you put in divided by the molecular weight. Gives you like how many chains. So the molecular weight dependence just by a factor of 1 because of the concentration effect going from single molecule to bulk. Right? So that's why the viscosity ends up being proportional to N. While tau goes with N squared. and then the friction factor, the diffusion coefficient is 1/n. And then, these are the Rouse predictions. So we know this viscosity with n. You can use, I mean, in bulk samples, you can usually get that log viscosity, plateau viscosity log molecular weight, and you get 1. That's the Rouse region. And we get 3.4, and that's the entanglement. That's the entanglement molecular weight is the cutoff of that. So we know that viscosity 1 thing is right. We know that's what we're looking for actually. So we have that. Then the tau to n squared can be easily demonstrated. So can the diffusion. So these are for chains below 10,000 grams per mole. That's like the cutoff for this. So it's basically Rouse, I guess, had a big argument about this. Like this is a Zem model. This is a Rouse model. Rouse thought that this thing was for dilute solution in his paper, his original paper. It turns out other people said, no, this thing, like this Beaucage guy and some other people said, no, this thing is for actually low molecular weight melts, like when the thing's below 10,000, we have this power 1 thing. So there's some argument about this business back in the 50s, whatever. So anyway, this is for a melt, polymer melt when the molecular weight is low. That's when this thing applies. Or if you're like inside a tube, so you have the entanglement tube and the chains inside the tube, it follows Rouse dynamics within the tube. So there's places where it's useful, but not for the thing that Rouse derived it for, which is dilute solution. In that case, you have this hydrodynamic effect. So the hydrodynamic effect is probably what's going on in this thing. Like he's got just the cluster, and then he's got the rods and the sheets, and somehow these things have more kind of hydrodynamically held polymer on it. Something's going on. But he argues that this is because the polymer has an interaction. But it can't, because he has a repulsive relationship between the polymer and the filler. So that argument seems to be wrong. I mean, you guys might find out that it's true, but one of the questions is about, I guess it's okay. So anyway, so he does that tau versus P, he finds that it's 2, and then the 2 kind of falls apart when he gets, so here, these are different number of particles. So he gets a larger number of particles, it falls apart, 2.42. Then in table 1 and 2, he shows also this, just going completely after this tau and then against the modes and the power, which is -2 for Rouse. So he's got nanoparticle, nanorod, nanosheets. When he gets to large volume fraction, he gets a problem. It deviates from 2. And he claims, like when he gets large aspect ratio, or large kind of size, which means aspect ratio, he also gets a larger than 2. But see his error bar, so it's 2.03 to 2.12 or something, right? So it's close enough to 2. But basically, he says that's significant. It's nice that he gives error bars. I mean, so, but I think that LAMP's program spits out error bars, so it's kind of like didn't have any choice. Anyway, so there's a lot in this thing. Actually, I mean, thinking that it was pretty simple, but so it's got the pain effect. This is the complex modulus versus composition. I don't know what this plot is actually. That one didn't make that much sense to me. I didn't look at it that long either. This is a correlation function, so I don't think I asked about that. And then the power 2 business, then he's got this thing. So this is also kind of puzzling. So he's got the coil size. You can measure the coil size of the simulated chains. And then if they're nanoparticles, so clusters, as you add more filler, the rate of gyration changes of the chain. So the chain molecular weight staying the same, you're just adding more filler into the system. That changes the rate of gyration of the chains. In a system where the chains are repelling the fillers, like there's no reason it's not like the chains are lying down on the filler particle, straightening out or something, or somehow clustering on it. They're actually not interacting or being repelled by it. So how the rate of gyration and distance change, like with filler concentration, is kind of weird. So it's got to be a confinement effect, some kind of confinement effect. It happens in different directions. So they get larger when they're clusters and smaller when they're aspect ratios. You can figure out that. There's a question about that. And then this is as he changes the filler size, how does this rate of gyration change? Would have been nice if you'd put error bars on these numbers, because it might be the error bar is so large it's meaningless, but especially where it goes up and down, you know, like, is that relevant? But anyway, so the particles show kind of not much change, and then the other two show these changes in the size of the chains. I don't know why that happens. I think I hinted at why it happens. There's a question about that. And then because he's doing an oscillatory, so he's doing the shear back and forth. So you can see you can calculate the energy. So you, like, when you go through that shear, so you can calculate the energy, like the energy between the NN energy between particles, then the PP energy, and then the NP energy. So you've got three energies in the cycle, right? So how much does, like, yanking on it change the energy of the system? There's how energy are you pumping in when you pull the thing, right? And how does that, so you can average over all those interactions in the simulation. Again, LAMP spits this out, so he doesn't need to do much. Anyway, so it turns out that the, which is which here? There's the three energies. So the change in energy is the difference between the peak and valley during the cycle of the oscillation. And then you can see, like, the Polymer nanofiller energy increases with shear amplitude. These all kind of indicate that there's some interaction. So he's got the Polymer filler, Polymer. Even the Polymer increases with shear amplitude. So there's something kind of weird about this, like, that isn't exactly explained that well. But so you can look at it and kind of figure it out. I think that's mostly what's in here. So that sufficiently took up a class. So mostly, like, take a look at this, and then there's this Strobel book, like, just look through that section and just go through his derivation, just copy it over, basically. That's what I did too. I mean, I just kind of went through that, just what I just did, you know. So, and then get to the point where you can say, yeah, tau should go with M, with this mode number to the -2, which is the thing he's trying to show in the paper, you know. So just so you kind of understand roughly where that came from. And the other things, it's difficult to get, even this is already, like, simplified, because this was done in tensors and he's turned it into, like, linear. So anyway, it's a little bit dicey stuff, the Rouse thing, but it's good to look at it. Like, you'll see it over and over again. Like, they'll say the molecular weight of viscosity goes power 1. Like, where did that come from? Right, so you can kind of get a rough idea where it came from. But to really do it, I think you'd need, like, a full course in it to really figure it out. And it wouldn't be worth it, because basically it's just that prediction. The prediction isn't that surprising. It's basically like, add another car onto the train, then it's harder to pull it. That's the Rouse result, right, for viscosity. It just goes up with the molecular weight. So there's nothing fancy about it, really. But it is a nice, if nothing else, it introduces you to the idea of the Debye heat capacity, which is probably more important in some ways than this. But anyway, so we can call it quits. Alice's questions about anything. But hopefully you get something out of this. So it'd be like nobody showing up today. It's like, I think that just, I don't know, the weather stinks too. You'd think that that would be, yeah, it's lousy out. So if it was warm weather, I'd say, like, people are out on the beach or something, but